What if you could travel so fast that time itself began to bend around you? What if a journey that feels like 1 year to you becomes 7 years for everyone you left behind? And what if the faster you move, the more the entire universe ahead of you begins to collapse into a tunnel of light? Right now, something like this is already happening. Not in science fiction, not in theory, but in orbit above your head. A clock aboard the International Space Station ticks slightly slower than the one on your wrist. The astronauts on the station are moving at roughly 17,500 miles per hour as they circle the Earth. At that speed, the effect is tiny, just a few milliseconds over months, but it is measurable. Atomic clocks confirm it with extraordinary precision. Time aboard the station really does pass more slowly. The difference is small, but it is the faintest hint of something far stranger hidden inside the structure of the universe. Because if you continue increasing that speed, the effect grows, and it grows very quickly. At 10% of the speed of light, time begins to shift just slightly. A clock moving at that speed ticks a fraction slower than one at rest. At 50% of the speed of light, the difference becomes obvious. Time on the moving ship flows noticeably slower than time back home. At 90%, the gap becomes dramatic. At 99%, it becomes almost unbelievable. Travel at that speed for 1 year, and more than 7 years will pass on Earth. Push even closer. 99.999% of the speed of light, and the ratio explodes. 1 year for you could mean 200 years for the rest of the world. Your friends would grow old, civilizations might change, entire generations could pass, and you would only experience a single year. This is not speculation. This is not hypothetical. This is exactly what Einstein's equations predict. But time slowing down is only the beginning. Because as you approach the speed of light, the universe does not just alter the flow of time. It begins to reshape space itself. Distances ahead of you shrink. Objects compress along your direction of motion. Stars shift position in the sky. The faster you move, the more extreme these distortions become. Eventually, something extraordinary happens. The entire night sky begins to collapse forward. Stars that should appear beside you begin sliding toward the front of your ship. Constellations stretch and distort. Light from distant galaxies compresses to higher and higher energies. Ahead of you, the universe concentrates into a blazing circle. Behind you, the sky fades toward darkness. This transformation is not an illusion. It is the result of one of the most profound discoveries in the history of science. The discovery that space and time are not fixed. They are flexible. They stretch. They contract. They warp, depending on how fast you move. But before we can understand why this happens, we need to understand something even more fundamental. A number. A single number that sits at the foundation of everything in the universe. It does not depend on temperature. It does not change with location. It does not shift based on who measures it. Every observer, everywhere in the cosmos, agrees on its value. That number is 299,792,458 meters per second, the speed of light in a vacuum. To put this into perspective, light travels fast enough to circle the entire Earth 7.5 times in a single second. A beam of light leaving the moon reaches Earth in just 1.3 seconds. Sunlight crosses the 150 million kilometers between the Sun and Earth in a little over 8 minutes. This speed is so large that for most of human history, if people believed light traveled instantly, it simply appeared everywhere the moment it was produced. After all, when you flip on a light switch, the room illuminates instantly. There is no visible delay. For centuries, this seemed perfectly reasonable, but the truth turned out to be very different. Light is not instantaneous. It has a speed, a finite speed, and discovering that speed would lead scientists to uncover something far more profound. Because the speed of light is not just fast, it is special. In fact, it is the ultimate speed limit of the universe. Nothing carrying mass can travel faster. Not a spaceship, not a particle, not even information itself. And the closer you try to get to that speed, the stranger reality becomes. Time slows, distances shrink, energy requirements explode, and the universe begins to resist your acceleration more and more violently. Imagine trying to push a car faster and faster, only to discover that the harder you push, the heavier the car becomes. At first, the resistance grows slowly, then faster, then dramatically, until eventually pushing it even a tiny bit faster would require more energy than exists in the entire universe. That is what happens as you approach the speed of light. The laws of physics themselves begin to push back. Yet the universe is structured in such a way that reaching the speed of light would require infinite energy, not a very large amount, not an impractical amount, but literally infinite, which means the final step, from almost the speed of light to exactly the speed of light, can never be taken. But this raises an obvious question. If nothing can reach the speed of light, why does light travel at that speed so effortlessly? And why does the universe treat that number as something so special? The answer to that mystery begins centuries ago with a simple question that puzzled philosophers, astronomers, and physicists for generations. How fast does light actually travel? For thousands of years, nobody knew. And when scientists finally began measuring it, their discoveries would trigger a chain reaction that would eventually rewrite our understanding of space, time, and reality itself. Because hidden inside the speed of light was a secret that no one expected, a secret that would reveal the universe is far stranger than anyone had ever imagined. And it all began with a lantern experiment on a hilltop. For most of human history, people believed something that now seems impossible. They believed light traveled instantly, not fast, not extremely fast, but infinitely fast. The idea seemed perfectly reasonable. After all, when you light a candle in a dark room, the illumination appears everywhere at once. There is no delay your eyes can detect. Ancient philosophers debated the question for centuries. Some suspected light might have a speed. Others argued it must be instantaneous. Among the most influential voices was Aristotle, who believed light required no travel time at all. According to him, illumination simply appeared everywhere the moment a source was created, and for nearly 2,000 years, and no experiment could prove otherwise. The problem was simple. If light did have a speed, it was far too fast for the tools of ancient science to measure. Even early scientists struggled with the challenge. In the early 1600s, Galileo Galilei attempted one of the first real experiments designed to measure the speed of light. His method was surprisingly simple. Galileo positioned two observers on distant hilltops, each holding a lantern with a shutter. The plan worked like this. One observer would uncover his lantern, sending a flash of light toward the other hill. As soon as the second observer saw the flash, he would uncover his own lantern in response. Galileo would then measure the time delay between the two flashes. If light had a measurable speed, there should be a detectable delay between the signals. But the experiment failed. Not because the idea was wrong, because human reaction time was far too slow. Light crossed the distance between the hills so quickly that the delay was completely hidden within the fractions of a second it took the observers to react. Still, Galileo reached an important conclusion. Light was not instantaneous. It was simply too fast to measure with the technology of his time. For decades, the question remained unanswered. Then, in the late 1600s, the solution came from a place no one expected. Not from Earth, but from the motion of a moon orbiting Jupiter. The discovery was made by a Danish astronomer named Ole Romer. Romer was studying Io, one of Jupiter's moons. Io regularly passes behind the giant planet, disappearing from view before emerging again on the other side. These eclipses occur at extremely predictable intervals. Astronomers could calculate exactly when each eclipse should occur. But Romer noticed something strange. The timing wasn't perfectly consistent. As sometimes Io's eclipse occurred slightly later than predicted. Other times, it happened slightly earlier. At first glance, this looked like an error in the calculations, but the pattern repeated, and the pattern had a very specific relationship with the motion of the Earth. When Earth was moving away from Jupiter in its orbit, the eclipses appeared late. When Earth was moving toward Jupiter, the eclipses appeared early. Romer realized something remarkable. The moon's orbit wasn't changing. The distance the light had to travel was changing. When Earth moved farther from Jupiter, the light from Io had to cross a greater distance to reach us. That additional distance caused a delay. When Earth moved closer, the light had less distance to travel. The delay disappeared. In 1676, Romer announced a revolutionary conclusion. Light does not travel instantly. It has a finite speed. Using the changing distance between Earth and Jupiter, he estimated that light takes about 22 minutes to cross the diameter of Earth's orbit. His calculation corresponded to a speed of roughly 220,000 kilometers per second. It wasn't perfectly accurate. The real value is about 300,000 kilometers per second, but Romer's estimate was close enough to destroy the ancient belief that light traveled infinitely fast. For the first time in human history, the scientists knew something profound. Light had a speed, and that speed could be measured. Over the next 2 centuries, scientists began refining the measurement. In 1728, astronomer James Bradley discovered a phenomenon known as stellar aberration. Because Earth moves through space while light from distant stars travels toward us, the apparent position of stars shifts slightly throughout the year. By measuring this shift, Bradley produced a more accurate estimate of the speed of light. Later experiments moved from astronomy to laboratory measurements. In 1849, French physicist Hippolyte Fizeau devised a clever mechanical experiment using a rotating wheel with teeth cut around its edge. A beam of light passed through the gaps between the teeth, traveled to a distant mirror, and returned. If the wheel rotated at just the right speed, the returning beam would be blocked by the next tooth. By carefully measuring the rotation rate required to block the returning light, Fizeau was able to calculate the speed of light with impressive precision. Just over a decade later, another French physicist, Léon Foucault, improved the method by using a rapidly spinning mirror instead of a toothed wheel. His experiment produced a value remarkably close to the modern measurement. By the late 1800s, physicists knew the speed of light with extraordinary accuracy. But something even more important had happened along the way. In 1865, a Scottish physicist named James Clerk Maxwell published a set of equations describing electricity and magnetism. These equations revealed something astonishing. Oscillating electric and magnetic fields could propagate through space as waves. And when Maxwell calculated the speed of those waves, he discovered something extraordinary. They traveled at exactly the same speed as light. This meant light was not just illumination. Light was an electromagnetic wave. Electricity, magnetism, and light were all part of the same phenomenon. It was one of the greatest unifications in the history of science. But Maxwell's discovery raised a troubling question. Every wave, scientists knew, required a medium. Sound waves travel through air. Water waves travel through water. ocean waves travel across the surface of the sea. Oh, so if light was a wave, what was it traveling through? Space appeared to be empty, yet Maxwell's equations said light waves were propagating through it. Physicists needed an explanation, so they invented one. They proposed that all of space was filled with a mysterious, invisible substance, a substance that could carry light waves the way air carries sound. They called it the luminiferous ether. According to this idea, the ether filled every corner of the universe. It was perfectly transparent. It had no detectable weight, and it remained completely stationary as planets moved through it. Light waves rippled through this invisible ether as they traveled through space. The theory seemed elegant. It explained how waves could move through empty space, and for decades, physicists accepted the ether as a fundamental part of reality. But there was one small problem. If the ether existed, Earth should be moving through it. And if Earth was moving through the ether, then the speed of light should change depending on the direction it was measured. Imagine riding a bicycle into the wind. When you ride against the wind, the air hits your face harder. When you ride with the wind, the air feels weaker. If Earth moved through the ether, light traveling in different directions should behave the same way. Light moving in the direction of Earth's motion should appear slightly slower, while light moving perpendicular to that motion should appear slightly faster. The difference would be tiny, but with careful instruments, it should be detectable. And in 1887, two American physicists decided to try measuring it. Their names were Albert Michelson and Edward Morley. They designed one of the most precise experiments ever built, and the result they discovered would shake physics to its core. Because when they finally measured the speed of light in different directions, they found no difference at all. None. Zero. And that single result would force scientists to confront a terrifying possibility. The entire understanding of space and motion might be wrong. In the next part of this story, we will see how that single experiment triggered one of the greatest revolutions in the history of science. As a revolution that began with a 26-year-old patent clerk who dared to ask a question no one else had considered. What if the problem wasn't with the experiment? What if the problem was with space and time themselves? By the late 1800s, physics seemed almost complete. Scientists believed they understood the fundamental structure of reality. Newton's laws explained motion. Maxwell's equations explained electricity, magnetism, and light. The universe appeared elegant, predictable. And if the ether existed, Earth had to be a planet in a solar system, in a galaxy, in a universe. And if the ether existed, Earth had to be moving through it. After all, our planet orbits the sun at about 30 kilometers per second. If the ether filled all of space and remained stationary, then Earth would constantly be drifting through this invisible medium, which meant something important should happen. Light traveling in the direction of Earth's motion should move slightly slower relative to Earth. Light traveling perpendicular to that motion should move slightly faster. The difference would be extremely small, but with precise instruments, it should be detectable. Two physicists decided to test this idea. Their names were Albert Michelson and Edward Morley. Michelson was already famous for building some of the most precise optical instruments in the world. Morley was an expert experimentalist with extraordinary patience and skill. Together, they designed an experiment that was almost unbelievably sensitive. Their instrument was called an interferometer. The principle behind it was simple, but powerful. A beam of light would be split into two separate paths using a partially reflective mirror. One beam would travel in one direction. The other beam would travel at a right angle to the first, and both beams would bounce off mirrors and return to the point where they were split. When the beams recombined, they would produce an interference pattern, a series of bright and dark fringes created by the interaction of the two light waves. If the two beams had traveled different distances, or if one beam had moved slightly faster or slower than the other, the interference pattern would shift. Even the tiniest difference could be detected. De Michelson's interferometer was so precise, it could measure changes in distance smaller than the width of a single wavelength of light. If Earth was moving through the ether, the interferometer would detect the difference. One beam would effectively be traveling slightly against the ether wind. The other would move across it. Their travel times should be slightly different, and the interference pattern should shift. In 1887, Michelson and Morley performed the experiment. They placed their interferometer on a massive stone table floating in a pool of mercury to eliminate vibrations. They rotated the entire apparatus slowly to test light traveling in different directions relative to Earth's motion. They measured the interference patterns again and again. Morning, afternoon, summer, winter, different orientations, different times of year. If the ether existed, the pattern would change as Earth moved through it. But something strange happened. The interference pattern never shifted. No matter how carefully they measured, no matter how they rotated the instrument, no matter what time of year they performed the experiment, the speed of light remained exactly the same in every direction. The ether wind they expected to detect simply wasn't there. The result was shocking. If the ether existed, the experiment should have detected it, but it didn't. The speed of light appeared to be identical in every direction, regardless of Earth's motion. This result was not just inconvenient, it was catastrophic. Because classical physics depended on the idea that velocities simply add together. If you stand on a train moving at 60 miles per hour and throw a ball forward at 30 miles per hour, the ball moves 90 miles per hour relative to the ground. This rule works perfectly for everyday objects. But Michelson and Morley had just shown that it did not work for light. If a source of light is moving toward you, the light does not arrive faster. If the source moves away from you, the light does not slow down. No matter how fast the source moves, light always travels at the same speed. This made no sense under Newtonian physics. For nearly 2 decades, the greatest minds in physics struggled to explain the result. Some scientists tried to save the ether theory. A Dutch physicist named Hendrik Lorentz proposed that objects moving through the ether might actually shrink slightly in the direction of motion. If measuring rods themselves contracted, the effect of the ether wind might be hidden. Around the same time, an Irish physicist named George Fitzgerald independently proposed a similar idea. Their hypothesis became known as length contraction. According to this idea, objects moving through the ether would physically shorten just enough to cancel the expected measurement differences. The mathematics worked, but there was a problem. No one knew why this contraction would occur. It was a mathematical patch applied to a deeper mystery. Another brilliant mathematician, Henri Poincaré, explored transformations that preserved the constant speed of light. His work hinted that space and time themselves might be involved in the explanation. But no one had yet taken the final step. Then, in 1905, a young man working at the Swiss Patent Office published a paper that would change physics forever. His name was Albert Einstein. At the time, Einstein was only 26 years old. He was not a professor. He had no laboratory. He was not even working in a university. His job was reviewing patent applications for electrical devices, but in his spare time, he thought deeply about the strange results emerging from experiments like Michelson and Morley's, and he realized something that no one else had been willing to accept. Instead of trying to explain why the experiment failed, what if the experiment was correct? What if the speed of light really was the same for every observer, no matter how they were moving? Einstein made a radical decision. He abandoned the ether entirely. Instead, he started from 2 simple assumptions, at 2 statements that seemed almost innocent, but whose consequences would transform our understanding of reality. The first assumption was this: the laws of physics are the same in every inertial reference frame. In other words, No experiment performed inside a smoothly moving system can reveal whether that system is moving or stationary. A laboratory moving smoothly through space behaves exactly like one at rest. The second assumption was even more radical. The speed of light in a vacuum is the same for all observers. It does not matter whether the source is moving. It does not matter whether the observer is moving. Everyone measures the same value: 299,792,458 meters per second. These two assumptions seem harmless, but when Einstein followed them to their logical conclusion, something extraordinary happened. The only way both statements could be true at the same time was if space and time themselves were not absolute. Instead of being rigid, fixed backgrounds where events occur, space and time must be flexible. They must stretch and compress depending on motion. Time could slow down. Distances could shrink. Events that appear simultaneous to one observer might not be simultaneous to another. Einstein called this new framework special relativity. And the first strange consequence of this theory was something called time dilation. Moving clocks would tick more slowly than stationary ones, not because the clocks were broken, not because of measurement errors, but because time itself was flowing at a different rate. To understand how this works, imagine a simple clock built from nothing but light. A beam of light bouncing between two mirrors. Each bounce marks one tick. From the perspective of someone holding the clock, the light simply moves up and down. But if that clock is placed aboard a rapidly moving spacecraft, something remarkable happens, and the way that light travels will reveal that time itself must slow down. In the next part of our journey, we'll explore what actually happens when objects begin to move at a significant fraction of the speed of light. Because once speeds reach even 10% of light speed, reality starts behaving in ways that no human intuition evolved to understand. And by the time you reach 90% of light speed, the universe begins to look completely different. To understand why time slows down at high speeds, Einstein imagined a very simple clock. Not a mechanical clock, not a digital one, but a clock made entirely of light. Picture two mirrors placed parallel to each other, one on the floor, one on the ceiling. A pulse of light bounces between them. Every time the light hits the bottom mirror and returns to the top, that counts as one tick. From the perspective of someone standing beside the clock, the light travels in a straight line, up and down, up and down. Each round trip takes a fixed amount of time. Now imagine placing that clock aboard a spacecraft. At first, nothing seems different. From the astronaut's perspective inside the ship, the light still moves straight up and down between the mirrors. The clock ticks normally. But to an observer watching the spacecraft fly past at high speed, something strange appears to happen. The ship is moving forward. So, while the light travels upward toward the top mirror, the entire clock is sliding sideways through space. That means the light doesn't travel straight up and down anymore. Instead, it traces a diagonal path, up and forward, then down and forward again. And that diagonal path is longer than the straight vertical path inside the ship. But here's the crucial detail. The speed of light must remain the same for both observers. The person on the spacecraft and the person watching from outside must both measure light moving at exactly the same speed. If the outside observer sees the light traveling a longer path, but still at the same speed, then something else must change. The only thing that can change is time. For the outside observer, the light takes longer to complete each bounce, and which means the clock ticks more slowly. And if a clock runs slow, then time itself is running slower for the moving observer. This is time dilation, not a visual illusion, not a measurement error, but a real physical change in how time passes. The exact amount of time dilation depends on speed, and it's described by a quantity called the Lorentz factor. usually represented by the Greek letter gamma. The formula might look intimidating, but its behavior is surprisingly simple. At everyday speeds, gamma is almost exactly 1. That means time dilation is effectively 0. Cars, airplanes, and rockets all move far too slowly for humans to notice the effect. But as speeds climb toward the speed of light, gamma begins to increase. At first, slowly, then faster, then dramatically. Let's start with something that already feels unimaginably fast, 10% of the speed of light. And that's about 67 million miles per hour. At that velocity, the Lorentz factor becomes roughly 1.005. That means time aboard the moving ship runs about half of 1% slower than time on Earth. For every 200 seconds on Earth, about 199 seconds pass on the ship. The difference is tiny. You would never notice it in daily life. But it is measurable with precise instruments. To appreciate just how extreme this speed is, consider the fastest object humanity has ever built. NASA's Parker Solar Probe, launched to study the sun, holds the record. At its peak velocity, it reaches about 430,000 miles per hour. That's fast enough to travel from New York to Los Angeles in less than 20 seconds. It is the fastest human-made object ever created. And yet, compared to light speed, it's barely moving. 430,000 miles per hour is only about 0.064% of the speed of light. Not 6%, not even 1%, less than 0.1%. But to reach 10% of light speed, a spacecraft would need to travel roughly 156 times faster than the fastest machine humanity has ever built. And even at that incredible velocity, time dilation is barely noticeable. Now imagine pushing further, half the speed of light, 50% of light speed. At that velocity, gamma becomes approximately 1.155. Now the effects become impossible to ignore. Time aboard the ship runs about 13% slower than time on Earth. If 1 year passes on Earth, only about 10.5 months pass aboard the ship. Over a long journey, the difference becomes significant. Spend a decade traveling at half the speed of light, and you would return home to discover that more than 11 years had passed for everyone else. But time dilation is not the only strange effect. Something else happens as speed increases. Space itself begins to compress. This phenomenon is known as length contraction. Objects moving at relativistic speeds become physically shorter along the direction of motion. Not visually shorter, actually shorter. Imagine a spacecraft that measures 100 meters long when at rest. If that ship travels at 50% of the speed of light, observers watching from Earth would measure its length as only about 86 meters. The faster it moves, the greater the compression becomes. Importantly, the contraction occurs only in the direction of motion. The ship's width and height remain unchanged. Only its length shrinks. This effect has been confirmed repeatedly in high-energy physics experiments. When particles like protons are accelerated to relativistic speeds inside particle accelerators, their interactions behave exactly as if the particles have been compressed along their direction of motion. The predictions of relativity match the measurements with astonishing accuracy. And by the time we reach 90% of the speed of light, these effects become dramatic. At that speed, gamma rises to about 2.3. Time aboard the moving ship runs less than half as fast as time on Earth. 1 hour aboard the ship corresponds to more than 2 hours for observers back home. Length contraction becomes extreme. Distances in the direction of motion shrink to less than half their normal value. A journey that appears to span 100 light-years from Earth's perspective would measure only about 43 light-years from the ship's frame of reference. The universe itself becomes smaller for the traveler. But the strangest transformation is not in time, and it's not in distance. It's in the appearance of the sky. Because when you move at 90% of the speed of light, the stars themselves begin to rearrange. Light arriving from different directions no longer enters your eyes at the same angles. Instead, The apparent positions of stars begin sliding toward the direction you are traveling. Stars that should appear beside your spacecraft begin drifting forward. Stars behind you begin disappearing from view. This phenomenon is called relativistic aberration. It's similar to what happens when you run through falling rain. Even if the rain is falling straight downward, your forward motion makes it appear to slant toward you. At relativistic speeds, light behaves the same way, but the effect becomes far more dramatic. At 90% of light speed, a star that should appear directly to your side, at 90 degrees relative to your direction of motion, would instead appear shifted forward to about 26 degrees. The entire sky begins to compress toward the front of your spacecraft. And imagine standing inside a spaceship and watching the universe gradually collapse into a bright tunnel ahead of you. Stars cluster closer and closer together. Behind you, the sky grows emptier and darker. And this is only the beginning. Because when speeds climb to 95% and then 99% of the speed of light, reality begins to transform in ways that are almost impossible for the human mind to visualize. Time stretches, distances collapse. The sky itself compresses into a blazing circle of light, and the energy required to push your ship even slightly faster begins to explode. In the next segment, we will move into this extreme regime, into the final stretch before the cosmic speed limit. Because once you reach 99% of the speed of light, the universe begins to behave in ways that no human being has ever experienced. And the closer you get to that ultimate boundary, the more violently reality begins to resist you. By the time a spacecraft reaches 90% of the speed of light, reality has already begun to change in ways that feel deeply unfamiliar. Time slows dramatically. Distances shrink. Stars slide toward the front of the ship. But the transformation is only beginning. Because beyond this point, something remarkable happens. The strange effects predicted by Einstein's equations begin to accelerate. At first, the changes increase slowly, then faster, then with astonishing speed. Push the ship slightly faster, to 95% of the speed of light, and the Lorentz factor climbs above 3. Now time aboard the ship flows 3 times slower than time on Earth. 1 year for the crew corresponds to more than 3 years for everyone back home. Length contraction becomes extreme. Distances in the direction of motion shrink to roughly 1/3 of their normal values. A destination that appears 1,000 light-years away from Earth now measures only about 320 light-years from the perspective of the ship. The universe ahead of you is literally smaller. But the most dramatic change is not in time or distance. It's in what you see. As the spacecraft approaches these extreme speeds, the night sky undergoes a transformation no human has ever experienced. Stars begin sliding forward across the sky. Constellations distort and collapse. Light from every direction bends toward the front of the ship. This phenomenon is called relativistic aberration. It happens because when you move extremely fast, the angles at which incoming light reaches your eyes begin to shift. The faster you travel, the more dramatically those angles change. At 95% of the speed of light, nearly the entire visible sky has already been pushed into the forward half of the spacecraft's view. Stars that should appear behind you are dragged forward. Stars to the side crowd toward the center. The universe appears to fold itself into the direction of motion. Turn around and look behind the ship, and you would see something unsettling. The sky there is growing darker, not because the stars are gone, but because their light is being stretched to longer wavelengths. This brings us to another powerful relativistic effect. The relativistic Doppler shift. When a source of light moves toward you, its light waves become compressed. Their wavelengths shorten. Their color shifts toward the blue end of the spectrum. When the source moves away, the opposite happens. The light waves stretch. their color shifts toward red. At everyday speeds, this effect is tiny. But at relativistic speeds, the shift becomes extreme. Stars ahead of your spacecraft begin to turn blue. Yellow stars become blue-white. Red stars shift into the visible range and glow bright blue. Even faint infrared radiation begins sliding into the visible spectrum. The sky ahead becomes brighter and brighter. Behind you, the opposite transformation occurs. Light from stars behind the spacecraft stretches into longer wavelengths. Visible light becomes infrared. Infrared becomes microwave. Eventually, the light shifts completely outside the range that human eyes can detect. The sky behind you fades into darkness. The faster the ship moves, the stronger this effect becomes. At 95% of the speed of light, the entire forward sky begins to glow with an unnatural intensity. Because another phenomenon is now taking hold. It's called the relativistic headlight effect. When an object moves toward you at relativistic speeds, the radiation it emits becomes concentrated into a narrow forward cone. Energy that would normally spread in every direction gets compressed forward. This makes the region ahead of the spacecraft appear dramatically brighter, as though the ship is flying into a cosmic spotlight. Meanwhile, radiation behind the ship spreads out and weakens. The darkness behind grows deeper. Now imagine pushing even closer to the ultimate limit. 99% of the speed of light. At this velocity, the Lorentz factor rises above 7. Time aboard the spacecraft slows dramatically. For every 1 year experienced by the crew, more than 7 years pass on Earth. A traveler who spends a decade aboard the ship would return to find that over 70 years had passed at home. Children would be elderly. Cities might have transformed. Entire chapters of human history would unfold without them. And yet the traveler would have lived only 10 ordinary years. But the transformation of the sky becomes even more astonishing. At 99% of light speed, relativistic aberration compresses nearly the entire visible universe into a narrow cone directly ahead of the ship. Imagine extending your arm and holding a tennis ball at arm's length. Now imagine that the entire night sky, every star, every galaxy, every nebula, has been squeezed into the tiny circular region hidden behind that ball. Everything outside that small circle becomes darkness. The whole universe appears to exist inside a brilliant disk ahead of you. Inside that circle, the light becomes extraordinary, because the Doppler shift has pushed the wavelengths far beyond their normal range. Visible light from stars ahead is compressed into ultraviolet radiation. Infrared radiation shifts into visible light. Even the faint background radiation left over from the Big Bang, the cosmic microwave background, begins to change. Normally, this ancient radiation fills the universe at a temperature of about 2.7 Kelvin. Its wavelengths are in the microwave region, completely invisible. But when you move toward it at 99% of light speed, those wavelengths become compressed. Microwaves shift toward the infrared, push the speed even higher, and they shift into the visible spectrum. At extreme velocities, the ancient afterglow of the Big Bang would appear as a faint glow ahead of the spacecraft, the very birth of the universe becoming visible to the traveler. But there is a darker consequence hidden inside this transformation. Because as light compresses into shorter wavelengths, it also becomes more energetic. Radiation that was once harmless begins to grow dangerous. And at even higher velocities, the universe itself begins to turn hostile. Every photon ahead becomes more energetic. Every atom in interstellar space becomes a high-energy projectile. The faster you travel, the more violent the environment becomes. And meanwhile, something else is happening beneath all of this. Something even more fundamental. The energy required to push the spacecraft faster is rising dramatically. At first, the increase is manageable, but near the speed of light, the cost of additional speed begins to explode. Each tiny increase in velocity requires vastly more energy than the one before it. The closer you get to the cosmic speed limit, the steeper the energy curve becomes, until eventually something astonishing happens. The mathematics reveals that the final step, from almost the speed of light to exactly the speed of light, would require infinite energy. Not a very large amount, not a technologically difficult amount, but literally infinite. Which means that no matter how powerful your engines become, no matter how advanced your civilization grows, the speed of light itself can never be reached. And the deeper reason for that lies inside one of the most famous equations ever written, an equation that reveals why the universe has placed a permanent wall at the speed of light. In the final segment of this journey, we will explore that wall, why it exists, why no object with mass can ever cross it, and what this ultimate cosmic boundary reveals about the nature of reality itself. By the time a spacecraft approaches 99% of the speed of light, the universe has already transformed. Time slows, distances collapse. The sky compresses into a blazing circle of light ahead. But something even more dramatic is happening beneath all of these effects. Something hidden inside the mathematics of motion itself. Because the closer you get to the speed of light, you're pushing back harder. Until eventually, the universe begins pushing back harder. Until eventually, the resistance becomes overwhelming. The reason lies inside one of the most famous equations in physics. E equals gamma mc squared. This equation describes the total energy of a moving object. The symbol m represents the object's rest mass. C is the speed of light, and the mysterious symbol gamma, the Lorentz factor, measures how relativistic effects increase as velocity approaches the speed of light. At everyday speeds, gamma is almost exactly 1, which means the equation reduces to the simpler form many people know. E equals mc squared, the energy contained inside mass itself. But when an object begins moving at relativistic speeds, gamma grows larger. At 90% of the speed of light, gamma is about 2.3. At 99%, it rises to about 7. At 99.9%, it exceeds 22. At each step closer to light speed increases gamma dramatically. And since energy is multiplied by gamma, the energy required to keep accelerating grows just as quickly. At first, this increase seems manageable, but the mathematics reveals something extraordinary. When velocity reaches the speed of light itself, something strange happens in the equation. Gamma becomes infinite, not very large, not astronomically large, but literally infinite, which means the total energy required to reach the speed of light also becomes infinite. And infinite energy does not exist anywhere in a finite universe. This creates a permanent boundary. No matter how powerful your engines are, no matter how advanced your civilization becomes, you can approach the speed of light forever, but you can never reach it. The final step, from almost the speed of light to exactly the speed of light, requires an infinite amount of energy. This boundary is not a technological limitation. It is a feature of the geometry of space-time itself, and we know it's real. Because particle accelerators demonstrate it every day. Inside facilities like the Large Hadron Collider, protons are accelerated to speeds incredibly close to the speed of light. They reach velocities like 99.999999% of light speed. Yet despite enormous increases in energy, their speed barely changes. Instead of moving faster, the extra energy goes into increasing the particles' relativistic inertia. They behave as though they are becoming heavier, harder and harder to accelerate. The closer they approach light speed, the more stubbornly they resist further acceleration. And no matter how much energy scientists add, the particles never reach the speed of light. They only get closer and closer. This behavior has been confirmed countless times. But nature itself has produced even more extreme examples. In 1991, detectors in Utah recorded an incoming cosmic ray so energetic that physicists gave it a nickname: the Oh My God particle. It was a single proton traveling through space with an energy of roughly 50 joules. That might not sound impressive, but remember, a proton is a subatomic particle with a mass about a trillion times smaller than a grain of sand. Yet this single particle carried as much energy as a baseball thrown at 60 miles per hour. Its speed was so close to the speed of light that the difference was less than 1 part in a trillion. And even that extraordinary particle, accelerated by the most violent astrophysical events in the universe, still did not reach the speed of light. The gap remained tiny, almost unimaginably small, but still there. Closing that final gap would require infinite energy. But even if infinite energy somehow existed, another problem would appear. Because at extreme relativistic speeds, the universe itself becomes dangerous. Empty space is not truly empty. It contains a thin haze of atoms drifting between the stars. On average, about 1 hydrogen atom per cubic centimeter. At normal speeds, those atoms are harmless. But from the perspective of a spacecraft traveling near the speed of light, those atoms become something very different. Yet they become relativistic projectiles. Each atom slams into the spacecraft with enormous energy. At 99% of light speed, a single hydrogen atom striking the ship carries the energy of a powerful particle accelerator beam. Billions of these atoms would hit the front of the spacecraft every second. Each impact would generate showers of secondary particles. Radiation would flood the interior. Electronics would fail. And biological tissue would absorb lethal doses of radiation almost instantly. And the faster the ship moved, the worse the bombardment would become. Even the ancient radiation left over from the Big Bang, the cosmic microwave background, would transform into something dangerous. Normally, this radiation is harmless microwave energy, but at extreme relativistic speeds, the Doppler effect compresses those wavelengths. Microwaves become infrared. Infrared becomes visible light. Visible light becomes ultraviolet. At sufficiently high speeds, the cosmic microwave background would shift into X-rays and gamma rays. The ship would face a wall of high-energy radiation from the front. The universe itself would become hostile to any material object attempting to move that fast. But if nothing with mass can reach the speed of light, why can light itself travel at that speed so effortlessly? The answer is surprisingly simple. Photons, the particles that make up light, have zero rest mass. They are fundamentally different from particles like protons, electrons, or atoms. Massive objects follow paths through space-time where time flows normally, but massless particles follow a different kind of path entirely. They are born moving at the speed of light. They do not accelerate to that speed. They never travel slower. From the moment a photon is created, it moves at 299,792,458 meters per second. Always. For its entire existence. The speed of light is not just a number. It is the boundary separating two different kinds of motion through space-time. Massive objects move below that boundary. Massless particles exist on it, and nothing can cross from one side to the other. This raises an interesting question. Could advanced civilizations ever find a way around this limit? Science fiction often imagines technologies like warp drives or wormholes, Some theoretical solutions to Einstein's equations even describe space-time geometries that might allow faster-than-light travel. But these ideas require something we have never observed in nature: a substance with negative energy density, exotic matter capable of bending space-time in extreme ways. So far, no experiment has shown that such matter can exist in the quantities required. For now, the speed of light remains the deepest boundary we know. But that boundary does not mean the universe is unreachable. In fact, relativity reveals something remarkable. The faster you travel, the less time passes for you. Which means that even though you can never exceed the speed of light, you can still cross enormous cosmic distances within a human lifetime. A spacecraft accelerating comfortably at 1 g, the same acceleration you feel standing on Earth, could reach the nearest star system, Alpha Centauri, in about 3 to 4 years of ship time. Longer distances become possible too. The center of the Milky Way, 26,000 light-years away, could be reached in roughly 20 years for the traveler. But tens of thousands of years would pass on Earth during the journey. This is the true cost of relativistic travel. Not energy, not distance, but time. Every journey near the speed of light becomes a one-way trip into the future. You could cross the galaxy, but the world you left behind would be gone. Civilizations would change, languages would evolve, entire eras of history would pass while you traveled. The universe allows us to approach the speed of light, but it charges a price measured not in fuel, but in years. And yet, within that constraint, the cosmos remains astonishingly open. The speed of light may be an absolute boundary, but the space beneath that boundary is vast. A universe where time bends, where distance shrinks, where travelers who move fast enough can cross thousands of light years in a single lifetime. The wall at the speed of light is real, unbreakable, written into the geometry of space-time itself. But the universe it defines is still unimaginably large, and for any civilization bold enough to explore it, the stars are not forbidden. They are simply waiting for travelers willing to accept the rules of the cosmic road.